Okay, good morning, good afternoon, and good evening. Okay, getting close, so I'm going to give people just a few more minutes to filter in, although I'm not going to wait as long today as I often do, because today's a pretty packed lecture, so I want to try and get everything in if we can. Okay, as we're having people filter in, there were a few things that were left over from the last lecture that I wanted to mention. The first question that came up is string comparison and what order it's done. And I did look into this. The strings are compared, C++ strings are compared in lexicographic order, but not C strings and not string literals, because string literals turn out to be interpreted as C strings, not C++ strings, unless you explicitly cast them. And there's a really good Stack Overflow thread on this that I found I thought was really helpful, so I'm going to post that into the chat in case someone finds it useful to look in. The other thing that came up that I didn't have a good answer for last time was brace initialization versus parentheses initialization. And the key difference between brace and parentheses initialization is that brace initialization forbids narrowing. So for example, if you're supplying a double to a type that is an integer, in most other circumstances, that will automatically be converted by truncating the double. So narrowing, it throws away a little bit of the information of the double. If you use brace initialization, then that is an illegal initialization, because brace initialization does not allow for narrowing. And narrowing, I'll just add that into the... Narrowing is throwing away information. I saw a variety of opinions on this. Some people were pretty strongly in favor of always use braces. Some other people, there were some moments where maybe it wasn't a great idea. And I was pointed to a really great reference that talks about this and a lot of other things. This book is by Scott Myers, this Effective Modern C++. I have several of his books. I have this one. I haven't read it all yet. But he's excellent at being able to describe some of the trickier features of the language and why you might, or more importantly, might not want to use some of them. So I'll put that in the chat as well, in case someone would like to pick that up. I really like his writing, and I think he's really clear and concise, and I found it pretty helpful. Switching over to slides, it looks like I do have a little bit of a lag again between my tablet and the display, and I tried to restart it. I don't know what else to do, so hopefully it won't be too disturbing, but I'll try and be mindful of it as we go. So just to refresh your memory, so far we've been talking about data structures called trees. Trees are undirected, trees are fully connected but acyclic graphs. Most trees are directed in that they have a designated node that is the root. Roots can have children. Any node that has children is an internal node. Any node without children is a leaf node. And then we started talking about a particular data structure called binary search trees, where, and again, in a binary search tree, we have a node, and for every node, anything in its left subtree is strictly less than the value of the node, and anything in its right subtree is greater than or equal to the node. Greater than or equal to if duplicates are allowed, strictly greater than if duplicates are not allowed. So this is the basic data structure that we're thinking about. There's one other thing that I promised, which was to show you the recursive version of tree search. Remember, for tree search, we started a node. If it's the one we're looking for, oh, this is totally wrong. So I left the base case out. So if we found the node we're looking for, this is the node we're looking for. If we haven't found the node we're looking for, oh, and this is also wrong, because if not x, or, sorry, I should have paid a little more attention to this when I did it. So if x is the null pointer, we haven't found the node in the tree. Otherwise, if k happens to be equal to the node we're looking for, either way we'll return x. X is either the null pointer because we didn't find it, it's either the null pointer because we didn't find it, or it's the node that happens to hold the key if we did find it. If neither of those are true, it's not null and this isn't the node we're looking for, then if the key node we're looking for happens to be less than the current one, it's got to be in the left-hand tree, otherwise it's got to be in the right-hand tree. So that's the recursive version of the binary search tree search algorithm. The runtime of this is the height of the tree, because each time we're descending one level. The average case, in the average case, in nodes that were inserted in a sort of a random order with random values, we'll have a mostly balanced tree, which gives us logarithmic runtime. But in the worst case, we have a stick, a very unbalanced tree, that'll be linear time. And we'll talk a little bit more about how we get to either of those as we develop our notion of trees as we go along. So that brings us to how do we build these things? So we know how to search them. How do we build them? And it's very similar to search. And the idea is we're going to start at the root, and we're going to, if the root is where what we're looking for, or sorry, we're not searching anymore. We start at the root and we keep tracing a path through the tree until we find an empty spot where this node could legally go, and we'll put it there. So, for example, if we wanted to insert a node with a value 15 into this existing tree, well, 15 is greater than or equal to 15, so it's in the right-hand side. It's less than or equal to 18, so it would be in the left-hand side. It's less than or equal to 17. And so what we'll find is that, in fact, that is exactly where it goes. It belongs right there. So that's the basic idea and the example of how this does. And I'm also mindful that maybe I'm going a little bit fast, so I'm going to try and slow down a little bit. So let me take a deep breath, have a little tea, and then we'll move on. Now, when we think about this, the previous example we used talked about how to duplicate insertion, because we were inserting 15 into a tree that already has 15. If we don't have duplicates, then we're either going to return that we've already got the node in the tree, or it's strictly less than, or strictly greater than. If we have duplicates, we have to pick which side of the tree is going to have the equal, the values that are equal to the root. You could choose either one. The STL uses this side, and so that's the one we pick. So we are willing to, so we have to pick one particular way. The STL chooses this particular way. We're going to use the same way as we build out our binary search trees. Here's the code that does that. So we're going to insert, and one of the things I want you to pay particular attention to is that we're passing a pointer to a node by reference. So one of the things, whenever you see a complicated or a complex type signature, I tend to read them inside out. So X is a reference to a pointer to a node, which means that if we change the value of X, we will change the value of the pointer that was passed to us, not just a local copy, because it's being passed by reference, not by value. So if we found an open spot in the tree, this is where this node goes. This assignment will modify the version of the pointer that we were passed. And if this is an empty tree, that's the root pointer. So if it were an empty tree, the root pointer would point to our new node n. Now, if we haven't found a null pointer, we haven't found an empty spot in the tree yet, we have to keep looking until we find the empty spot. If the key we're inserting is less than the current key value, it has to be in the left-hand side of the tree. Otherwise, if it's greater than or equal to, it has to be in the right side of the tree. And these are just recursive calls. So we do a recursive descent through the tree, very similar to the way we saw insert work. And as soon as we find a null pointer, so if we have an arbitrary tree, and the node we're looking for belongs here, we'll create the node and set this child pointer to point it, because we're passing that pointer in by reference. So a little subtle, if you haven't seen pointers by reference before, it's a little bit subtle, and it's worth thinking about a little bit, and maybe even walking it through with a debugger to sort of convince yourself that it works the way you expect it to work. But the basic idea is that when we do this assignment, we're actually changing the value of the pointer that was passed to us, not our local copy. So here's the thing to try on your own. Start with an empty tree, insert these keys in this order, and draw that tree out. What do you get? Write a new order to insert exactly the same keys that generates the worst case tree. And remember, a worst case tree is a stick with no branches. And a really interesting question is, how many worst case trees are possible for n different unique values? So take a couple minutes, start working through the insertion, or if you'd rather, think about what, maybe just think about this question, or think about this question, and we'll take a minute or two for you to work through that if you'd like, and then I'll come back and we'll work through it together. Okay, so let's go ahead and look at it. So I forgot I did this. So let me just do the first few. We insert 12, that becomes the root. 5 is less than 12, so it goes here. 18 is greater than 12, so it goes here. 2 is less than 12 and less than 5, so it goes there. 9 is less than 12, greater than 5, it goes here, and so on. And if we keep building, this is the tree that we're going to end up with. So 12 is first, then the 5 goes here, 2. 18 is 3. The 2 to the right, that's the fourth node we insert. The 9 is less than 12, greater than 5, so it goes here. 15 is greater than 12, but less than 18, so it goes there. 19 greater than 12, greater than 18, it goes there. 17 greater than 12, less than 18, greater than 15, it goes there. 13 greater than 12, less than 18, less than 15, and it goes there, and that's the picture of the tree. And one of the things to notice about this tree is that it's kind of balanced. I mean, there are some pieces that are taller than others, but there's really not much you can do about it because everything above this line is completely full. That's a good sign. And these are both on the same level. That's also a good sign. That's not the only set of criteria we might care about for a balanced tree, but this is a really good one. So it turns out this order happens to have given us a tree that will behave pretty well because it's approximately log n high. Because the height of the tree is basically the cost of doing any search or insertion. Now, an order that inserts the keys that generates the worst case tree, just insert them in order. So 2 is the first one, 5 is greater than 2, 9 is greater than 2 and 5, 12 is greater than 2, 5, 9 goes there, 13 is greater than 2, greater than 5, greater than 9, it goes greater than 12, it goes there, and so on. And what we'll end up with is just one big straight tree, which is really a stick. What's interesting about this, though, is that that's not the only one, because we could do it in the opposite order. So if we said 19, 18, 17, so on, we'd get the same thing, except instead of a tree that goes off in this direction, we'd have a tree that goes off in the left, just in one straight line. And in fact, it turns out that there are lots and lots of ways to construct a really bad tree. And the way is that at each insertion, we pick either the largest or smallest that remain. And if we do that, so let's say we pick the 2 first, and then, so that's gone, then we pick the 19, that goes here, so that's gone, and then we pick the 18, it goes here, that's gone, and then we pick the 5, well, 5 is greater than 2, oh, no, this isn't quite right, huh, all right. I'll have to think about this more because now I've managed to confuse myself. Oh no, because I drew the tree wrong. Anyway, so now I've managed to confuse myself, and I don't want to unwind myself. I'll come back and post something on Piazza that talks about this because we do have a long lecture, and I don't want to get us bogged down into me confusing myself by not having enough tea. And yes, I am actually an equal opportunity caffeinator. I saw someone was on team tea. I'm also on team coffee. And yes, Shiv, that's exactly right. The tree becomes a stick that isn't straight. So that's kind of bad news because it turns out that there are about 2 to the n trees that are really bad for us. Now there are n factorial possible trees. N factorial is quite a bit bigger than 2 to the n. So most trees are pretty good, but there are enough trees that are bad that things get pretty evil. And so the complexity of all of our tree functions depend on this height of the tree. And again, if it's average, if we get them in kind of a random order, it's log n, but if we get a particularly bad order, and there are lots of particularly bad orders, we get a really unbalanced or stick, and it could be a jagged stick, that would work, but it could be pretty bad. And that gives us a linear depth. So what's average case? Well, random data in a random order is pretty average. And that's sort of the definition that we use for average, is a random set of data inserted in a random order. What do we get? Well, that's likely to be very well balanced, because there are many more things in n factorial than there are in 2 to the n. But there are enough bad spots that can get us into trouble. So we'll talk a little bit, we'll continue to flesh out how we work with regular binary search trees, and then we'll introduce a new kind of search tree that allows us to keep these things in balance, or at least approximately in balance. So here's another thing just to think about really quickly. How do we find the node with the smallest key? And what are the average and worst case complexities of that? Well, we sort of know the answer to this. The average and worst case complexities of anything to do with our tree is usually log n average, or linear if it's not. And so, but to find the tree that to find the node with the smallest key in the tree. Sorry, I got distracted by the questions in the chat. Thanks, Blake, for handling that. You just go to the left as far as you can until you can't go left anymore. So you start at the node, and if there's a left child, you go there. If that node has a left child, you go there. If that node doesn't have a left child, which 2 doesn't, 2 must be the smallest node in the tree. So to find the smallest node, you go left, left, left. And again, it's on average the height of the tree. In worst case, it's linear. So this is the function that does it. If the tree is empty, so this is going to be an iterative version of this function. If the tree is empty, well, there is no smallest node. But while there is a left child, we descend down the left side, and eventually we return the one that doesn't have a leftmost child. And again, average log n, worst case complexity n. Now it's a little bit of a setup to use Professor Darden's terminology, because we're going to come back to this idea. We're going to need this idea later in a second when we talk about removal. So how do we remove something? Well, if we're going to remove some random node in the tree, there are 4 possibilities. So we have a tree. If one of the things we're removing has no children, no problem, we just snip it off the tree. If one of the nodes we're removing has no left child, that's okay, we just cut it and replace it with its right child. If it doesn't have a right child, same thing, we just cut it and replace it with its left child. But what if we're trying to delete something in the middle that has 2 children? And there is a complete algorithm in the textbook that we use that's quite elegant, but we're going to walk through it today as well. And so the idea is we're going to need to find something below this node that we can replace here and make sure that the tree retains its sorted order, or its binary search invariant, that everything to the left is less than and everything to the right is greater than or equal to. Okay, again, easy case. If we're this is the node we're removing, it doesn't have a left child, we just replace it with the right child, and the right child might have children on both sides, totally fine. We're not losing any information because we just had something that didn't point to anything anyway, so it doesn't matter if we keep it around. Same thing if it happens to be the other way. If it doesn't have a right child, just replace it by the left child. So this is the one we're getting rid of. We just promote this up, and this, whatever was underneath it, continues to be underneath it. Everything is fine. And because everything in this subtree is less than z, it's less than z, but everything in this subtree is either less than q or greater than or equal to q, Well, everything here is still less than Q, and if everything in this subtree is greater than or equal to Q, this is still greater than or equal to Q. So no matter which way Q went, whether Z was the left child of Q or Z was the right child of Q, this promotion continues to obey the binary search tree invariant. Okay, the hard case. So there are left and right children, and so the idea is that you want to replace this Z with a way of combining the two. So Z has some left subtree and some right subtree, and it belongs to some other larger subtree. We know that everything to the left is less than or equal to Z. Everything to the right is greater than or equal to Z. Right? So if we find the smallest node, if we find the smallest node in that subtree, it's going to be sort of off in this corner, that node can replace Z. And this node can't have a left-hand subtree, because if it did, there would be a smaller node. Remember, the way we find the smallest node is go left, go left, go left, go left, go left, until we can't go left anymore. So since this doesn't have a left subtree, this can become its new left subtree, and everything is going to be fine. So this new node that we find, we call this the smallest successor of Z, that takes the place of Z, and then if it happens to have a right-hand child, that gets promoted into the node we just moved out of the way. Okay, so a little subtle, but we'll walk through the whole thing. And here's a picture example of this too. So we have the smallest. We want to remove V. We're going to go once to the right and then left as far as we can until we bottom out. That gets copied into the node we want, and then we trim it. Okay, here's the whole thing put together. So we're going to remove some node. We may need to find its in-order successor because the node that we remove may have a bunch of children. If the tree was empty, or we didn't find it, so we're looking for some value. If we never found the value in the tree, there's nothing to do because there's nothing to remove, so that's easy. Otherwise, if the thing we're looking for is less than the current node, it must be in the left-hand subtree. If the value we're looking for is less than val, well, then it must be in the right-hand subtree. And if we get to this point, we found the node. Okay, and one of the things I want to mention is that this seems a little odd that we do both of these in the opposite order. So val less than tree value and tree value less than val. That's an idiom that's common in the standard template library, because remember, operator less than is the one that our comparisons usually implement when we're providing custom comparisons. So if we get to this point, we have found the node, and we know which one we're trying to remove. Okay, here are the two simple cases. If the left pointer of the tree is null, so here's the node we're trying to remove, that's null, and there's a right-hand tree. Whoops, sorry. So this is the pointer T. We'll reset the pointer T to point to the left-hand node, and then we'll delete this node. And this covers the case when both of them are null as well, because if they were both null, V is the one we're getting rid of, V is null, and left is null, and right is null, well then this pointer will just be changed to null, and then we'll delete this node and everything is good. So this covers both also covers both of them being null sort of for free. This is the mirror case of that. So this is V is the node we're getting rid of. It has a left subtree, but not a right subtree. Same thing. We'll take the pointer that points to this node, we'll move it to point to the new left subtree, and we'll delete this node. So those are all the easy cases. Okay? The thing that's left is the hard case. So I'm going to walk through this one a little bit carefully. So here's the picture. We have a node V we want to delete. We have a pointer to it, which is tree. It has both a left subtree and a right subtree. Okay. So what we're going to do is we're going to look for the in-order successor. We're going to start to the right, which has to exist because we know the right subtree isn't null. If it was null, we would have already been done. And then we're going to go left as far as we can, which is what this line is saying. So while there is a left child, we're going to descend to the left. And we're going to go until we hit something that doesn't have a left-hand pointer anymore, but it might have a right-hand pointer, and we'll come back to that in a sec. Okay. We clone the value. Actually, let's not call it clone. Let's call it copy. We copy this value into V, and then we call ourselves again remove. Remember, the name of this entire function is remove. We're going to remove from tree right, from this tree. This is tree right. The in-order successor value, this one. And that one will be easy because we know that it doesn't have a left-hand child. It may have a right. We know it doesn't have a left-hand child. It may or may not have a right-hand child. And if it does, that right-hand child will become the new occupant of the old smallest successor. So this is a little subtle again, and it's worth walking through because understanding how this works will turn out to be pretty helpful to understanding a lot of things that you might be asked to do about trees. With that, I want to take a quick pause and see if there are any questions before we move on to the next topic, which is going to be how we manage to keep things balanced. So I'm going to take just a couple minutes, and I'll take questions in the chat, or if you want to just take a couple minutes to stand up and stretch, please feel free to do that. Okay, we have one question from Fawn. Can we explain why we go to the right at the beginning of else? We go to the right at the beginning of the else because we want the smallest node larger than or equal to the node we're deleting. So we have to go right first because this subtree is the subtree that is greater than or equal to. Could we have done the same thing with the largest value that is less than the node to the right? Not necessarily, no. Because if the largest value in the left subtree could be equal to something else higher in the tree, and if we promote it above, we will violate the left-hand subtree principle. So we're not allowed to do that. Okay. So coming back to just summarize where we are so far, binary search tree, every node has two children, a left or a right, possibly a parent. All of the nodes are ordered. Everything in the left subtree is less than the root, and everything in the right subtree is greater than or equal to the root. The modification to nodes, if we're messing around at the leaves, this is really pretty easy. If we're trying to modify something in the middle, things get a little more complicated, but doable. And in general, the operations are logarithmic in the average case and linear in the worst case. So the big question is, how do we make sure that we are in the average case even when we get a bad set of input? And that's going to be the next thing that we look at. So, AVL trees. AVL trees are a way of creating trees that no matter what order the nodes get inserted, the tree ends up being relatively well balanced. So it's a self-balancing binary search tree. And it's named for Adelson, Velsky, and Landis. And the idea is we're going to start with a binary search tree. And remember, the binary search tree has the following property, that this is less than, this is greater than or equal to. And then we're going to add an extra invariant, that the heights of these two trees, so this is H left, this is H, if I can manage to type correctly or draw correctly. This is H right, that the difference between those two is less than or equal to 1. So the heights at every node, the heights of each of its subtrees differ by at most 1. And what we're going to do is whenever we break this invariant, we're going to use a trick called rotations, where we reorder some things in the tree in a special way to correct the imbalance. And because we can do that, the absolute worst case search and insert will now be logarithmic, which is a huge win. So now we don't have to worry about linear worst case. The worst case will also be the average case, which is now the best case, which means every insert, every search, and it turns out every removal will be logarithmic in total costs. Okay, just as a reminder, tree height is measured upward from leaf nodes. An empty tree has height of 0. Every leaf node has a height of that's equal to 1. So there's a recursive formula. The empty tree has a height of 0. So the empty tree has nothing in it. Otherwise, the height of any node n is the max of its children's heights plus 1 for this node. Okay, this is something we talked about last week, and this is just a refresher of something that we've seen before. So the idea is that for every internal node of T, so we're going to look at these 4 examples, do the heights of the children differ by at most 1? Well, an empty tree, yeah, I mean, there are no children, the height is 0, there are no children to measure, So the empty tree is certainly a balanced AVL tree. If we insert 5, sorry, Darren, yes, that's the deletion in a non-AVL tree is linear in the worst case, because again, we could be deleting out of a stick, deleting at the root, have to go all the way down, or in any case, we have to do the search. For tree 1, well, the height of the left subtree is 0, the height of the right subtree is 0, 0 minus 0, absolute value is equal to 0, 0 is less than 1, so that one's good. Tree 2, the height of the 2 is 1, the height of the right subtree is 0, max 1 and 0 is 1, the height of 5 is 2. These two differ only by 1, so that tree is an AVL tree. Tree 3 is a little more interesting. So the height of 3 is 1. The height of 2 is the max of 0 and 1 plus 1, so that's 2. The height of 5 is the max of 0. Sorry. The height of 5 is the max of 0 and 2. So the height of 5 is 3. And this is not an AVL tree because 5's left subtree's height is 2 and its right subtree is 0, so that is not an AVL tree. Look at some more trees. Tree 4, and again, I'm going to go through these just a little bit more quickly. The height of that is 1, the height of that is 2, the height of that is 1, the height of that is 3. Everywhere, this only differs by 1, this only differs by 1, we're good. So tree 4 is good. The height of 3 is 1, the height of 6 is 1, leaves are automatically balanced. This is 2, 1 and 0 differ by 1, this is 2, 1 and 0 differ by 1, this is 3, 2 and 2 differ by 0. Tree 5 is good. Tree 6, this is 1, this is 2, those differ by 1, this is 1, this is 2, these differ by 1. The height of this is 3, but the height of this is 0. So at this point, tree 6 is not an AVL tree, therefore tree 6 is not an AVL tree at all. Now it turns out that the height of this is max 2 and 3 is, so the height of that is 4. So because this is unbalanced, this tree is not an AVL tree. So what we'll see is that there's some simple and elegant ways to be able to fix a tree as we're inserting things to be able to rebalance them. Because the idea is if we start with an AVL tree and we add a node, that's potentially going to make one subtree taller than another. And if the subtree that it makes taller was already 1 taller than the other, it's going to make it 2 taller than the other. And we're going to have to fix it at that point. Okay. It turns out this is going to be a very hand-wavy proof. This is not going to be a 203 or a 376 proof or a 477 proof, but we'll come back to it. So the basic idea, if h is the height of the tree, we're going to define the term n of sub h, which is the smallest number of nodes in an AVL tree of height h. And what we want to prove is that that's approximately h squared, which means that everything is approximately log n. So in an empty tree, obviously n0 is 0. The minimum number of nodes in an empty tree is 0. The minimum number of nodes that's 1 high is just a single node, 1. So these are the base cases of our recursive proof. So for any h greater than 1, the height of the tree contains the root node, 1 for the root node, an AVL and then a subtree of height h minus 1 on one side, and without loss of generality, we'll say that it's the left side. So this is h, this is h minus 1. And another subtree on the right whose height is h minus 2. And this has to be h minus 2 because if it were h minus 3, it wouldn't be an AVL tree. And if it were h minus 1, then there would be more nodes than we need. So one of these subtrees has to be h minus 1 and the other subtree has to be h minus 2. So we know that for any tree that's larger than 1 deep, the minimum number of nodes in that tree is that node plus the minimum number of nodes in a tree of height h minus 1 plus the minimum number of nodes of a tree of h minus 2. And this is a recurrence relation like a lot of others we've seen, and we'll solve it in pretty similar ways. And Joseph, if you're talking about the current tree, we're going to come back to that. Why don't you go ahead and chat with Blake about this a little bit, and then we'll come back and see if we can catch your question a little bit, but I want to keep talking about the proof, or the slide before. So the right subtree from node 7 no, the left subtree is 2. Yeah, I think we're going to tree 5. So no, you're looking at, this is the height, not the difference, because the height of the left subtree is 1, the height of the right subtree is 0, 1 minus 0 is 1, so this is balanced. Okay, coming back to our proof. So we have from the prior slide, h is the height of the tree, n of h is the minimum number of nodes. We know that n of h follows this. Now we also know that n of h minus 1 has to be greater than n of h minus 2, which means that n of h, there have to be at least 2 times n of h minus 2 nodes in the tree, because n of h minus 1 has to have at least as many nodes as n of h minus 2. And what that means is we can start doing an induction. So it's also greater than 4 of n h minus 4, and it's also greater than 6 of n h minus 6, and so on. The closed form solution of that, which I won't work out for you here, but I may follow up with a Piazza post, is that it's at least 2 to the h minus 1 total nodes. And remember, what we were looking for was something on the order of 2 to the h total nodes. And this is, because these are just some constant factors. So if we take the logarithm of both sides of these things, log n is greater than or equal to h over 2, log base 2 n of h is greater than or equal to h over 2 minus 1. And then we solve for that, and we end up that h is less than 2 of log n. So we know that the height of the tree, in other words, the height of the tree, if we have about n nodes, is about logarithmic. And again, I'm waving my hands very vigorously. This is not really a 203 or 376 proof, and the faculty who teach those courses would be aghast that I'm calling this a proof. So I may come back and follow it up or point you at a better one in Piazza later, but this is sort of good enough. So take it on faith for now, and we'll come back and see if we can come back to it. But the basic idea is, if something is an AVL tree, we know that its height, that its height is approximately logarithmic in the total number of nodes in the tree. So now the trick is we just need to be able to build these things. And that turns out to be a little tricky. Okay, so just how do we do AVL tree algorithms? Search is the same in a binary search tree. An AVL search tree is a binary search tree. We're not modifying it, so we can't modify the AVL property. So search just works the same as a binary search tree. The same with sorts. So if we're going to use an AVL tree to sort a bunch of numbers, we insert the nodes one at a time. But the worst case complexity of insertion is now log n. We're going to insert n of them. So it's order n log n to do all of the insertions. We're going to perform an in-order traversal. That's just linear because we're going to touch all of the nodes once. So it's O(n) log n plus n. We can get rid of that. So an AVL tree, using an AVL tree to perform a search can be done in n log n time, which is the don't pass go, do not collect $200. It's the fastest asymptotic search time you can have. Insert is trickier. So the basic idea is we're first going to insert as if we were a binary search tree, and if we break the AVL height invariant, we're going to rearrange the trees to rebalance the height. So every node needs to know its own height, and remember, as we insert going down, we can propagate any changes in height back up as our recursive algorithm unwinds. And as we unwind, we can compute the node's balance factor. So the balance of a node is the height of its left tree minus the height of its right tree. If it's negative, so it's left minus right. A negative is also called right heavy. A positive tree is called left heavy. And if they're equal, then they're equal. So if the balance, a node is AVL balanced if and only if its balance is either 0, which means both subtrees are equal in height, positive, which means left is taller by 1 or left heavy, negative is right is taller by 1 or right heavy, and if the absolute value of these is greater than 1, so if it's +2 or bigger, or -2 or smaller, then that node is out of balance and we have to fix it. Okay, so let's take a look at a little bit of these. So what I'm going to do is I'm going to walk through the heights first in red, and once I compute all of the heights in red, I'll compute the balance factors in blue. So the height of node 3 is a 1. So the height of node 2 must be 2 because it's the maximum of its children plus 1. The height of node 7 is a 1. It's a leaf. The height of node 5 is the max of its children plus 1. That's 3. The balance factor at node 5 is the balance factor at node 3 is 0 because 0 minus 0 is 0. The balance factor at node 2 is 1 because 0, remember this is 0. 0 minus 1 is minus 1. The balance factor at node 7 is 0. 0 minus 0 is 0. The balance factor at node 3 is not minus 1 minus 0, which would be minus 1. It's 2 minus 1. So 2 minus 1 is plus 1. Okay. Do the same thing for the tree on the right-hand side. I'm going to go a little faster. The leaves are always 1 because their children are 0 on each side. 1 plus 0 is 0. 3's height is 2. 2's height is 3. 5 is the max of 3 and 1. Plus 1 is 4. And now the balance factors at each node, well, the balance factors of leaves are always 0. The balance factor of 3 is 0, 0 minus 1, negative 1. The balance factor at node 2 is 0 minus 2, which is negative 2. And the balance factor at the root is 3 minus 1, which is 2. So there are two different nodes that are out of balance. The node with value of 2 is out of balance, and the node with value of 5 is out of balance because the absolute values of their balance differences is greater than 1. Okay. We can do the same thing in a slightly more complicated tree. Label the balance factor on each node. So, and I'll just draw the heights off to the left. So this is height 1. Well, actually, that's not going to work. So This is height 1. So all the leaves are height 1. Everything that's a parent of a leaf is 2. This is 3. This is 4. And then if I were going to compute the balance factors, well, the balance factor of all the leaves is always 0. 1 minus 1, that balance factor is 0. 0 minus 1, that balance factor is -1. 2 minus 2, that balance factor is 0. 1 minus 1, that balance factor is 0. 3 minus 2, that balance factor is 1. So this tree is, in fact, balanced. Okay, what if we inserted? And again, it begins just like the binary search tree. So if we're going to insert node 14, well, 14 is less than 15, so it has to go to the left. 14 is greater than 6, it has to go to the right. 14 is greater than 7, it has to go to the right. 14 is greater than 13, so it belongs down here. However, once we do that, then this node becomes out of balance. Sorry, I got a little enthusiastic about what I was doing. So the node at 7 becomes unbalanced because the height of its left subtree is 0, the height of its right subtree is 2, that's a -2. And the node at 15 is unbalanced because the height of its left subtree is 4, 1, 2, 3, 4. The height of its right subtree is 2, that's also a -2. So bad news. So once we do this insertion, we're going to have to fix it. And the idea is that we're going to use rotations, this idea of rotations, to rebalance the binary tree. So to do that, we're going to swap a parent and one of its children, preserving the binary search tree ordering. So we're going to swap 2 with 3, but because 2 is less, we're going to swap 2 with 3, but because 2 is less than 3, it's going to have to become 3's right-hand child. So this rotates in this direction, and that gives us this tree. So the new child of 5 is 3. 3, this node swaps down, and we end up with a balanced tree. So what's really interesting about rotation is that it's a local change that involves at most 3 pointers and 2 nodes. And we'll see why when we talk about that in a minute. But this is really important because if it's 3 pointers and 2 nodes, that's 5 things. 5 is independent of n. That means rotations happen in constant time relative to the size of the tree. Okay, so 1 rotation happens in constant time. So that's going to turn out to be really, really important for us as we keep working through this. Okay, so as I said before, this is just restating the prior slide. We're going to use rotations to rebalance the binary tree. We're going to interchange the role of a parent and one of its children, preserving the order, which means the old parent has to become a new parent. If the old child was to the right, the old parent has to be to the left. If the old child was to the left, sorry, can't do it. If the old child was to the left, the new parent has to be to the right. It's hard to do when I'm trying to see this in the camera and mirrored. The second part, this preserving the BST ordering, is a little bit tricky. So a right rotation, we copy the right pointer. So here's the left child, here's the right pointer. We copy the right pointer of the left child to be the left pointer of the old parent. And for a left rotation, we do it in the opposite. The right child, left pointer, becomes the left pointer of the right child becomes the right pointer of the old parent. And this is what this looks like in pictures. So if we're going to rotate right, around P, then the right child, the right pointer of the left child becomes the left pointer of the old parent. And because this was in between, so everything in here is less than P, but it's greater than or equal to LC, because that's where it is. Well, everything in that tree is still greater than or equal to LC, and it's still less than P. So this preserves the binary search tree order. And the same thing happens if we rotate left. So if we rotate left, the left subtree of the right child will become the right subtree of the old parent. This fell between the parent and the right child before. It is still going to fall between the parent and the right child when we're done. So either way, when we rotate right and rehome the old left-right subtree as the parent, or we rotate left and we rehome the old right-left subtree as the parent, then we preserve the order of the tree. And the question of how do we know where to move the parent, Samuel, is whether we're rotating a right or a left. And we're going to rotate right if this is too tall, and we're going to rotate left if the right is too tall. Because rotation can, but doesn't always, shorten the length of the heights of subtrees. Okay? So let's take a look at this. So imagine we were going to try and use a rotation to balance this tree. So for this one, we're going to rotate left. Remember, I have left and right, and I can't ever remember. So this is going to rotate to the left, which means B becomes the new parent. B's right subtree, or B's left subtree, is empty. And so that becomes the right subtree of the old parent. Okay, we could try and do the same thing here. If we were going to rotate to the left, well, C becomes the new node. C's right subtree is B. So B becomes the new left subtree of A. Now this works because this is balanced. This really doesn't help us. So, and this is that same thing in pictures. If we have a stick, a straight line stick, a single rotation will solve our problem for us. So a straight line stick has an imbalance because one side is 0 and the other side is 2. For a straight line stick, a single rotation, in this case a rotate left at A, solves our problem. A jagged stick needs 2 rotations. The first one, a right rotation at C to give us a straight line stick, and then a left rotation at A to fix the overall imbalance. So if we have a jagged stick to the left, we're going to rotate this way, which gives us a straight line stick, and then we're going to rotate this way, which gives us a balance. Okay, so when we have a straight stick, we only need 1 rotation. If we have a jagged stick, so either a straight stick in one direction or the other, 1 rotation solves our problem for us. But if we have a jagged stick, we're going to need 2 rotations. The first to convert it into a straight stick, and then the second one to fix the straight stick. Okay, we call these double rotations. So there are 4 cases where we might be inserting and end up making things bad. So if we insert, so the first thing is if we're inserting into something that doesn't have, if we're inserting into a node that has no children on either side, then it doesn't matter and we're fine. That insertion just works. If we're inserting into a node, sorry, that's not true. If we're inserting into a node that doesn't leave things out of balance, we're fine. If it does leave things out of balance, there are 4 things we might have done. A straight stick to the right, which needs only a single right rotation. A straight stick to the left, which is a single right rotation. Let me see if I can remember which ones these are. So if we're rotating left, a stick to the left and right. No, that's wrong. So if we have a stick to, yeah, no, that was right. That was right the first time. The stick to the right and to the left. We're going to do a left rotation at the child, which gives us a stick to the left, and then a right rotation, or sorry, a left rotation and then a right rotation at the node, which gets us to where we were going to go. If we have a stick the other way, we need to rotate this, which gives us a stick, and rotate this, which gives us the thing we were looking for. This is the same thing in pictures. So in this case, this tree is 2 bigger than this tree, but it's left, so it's unbalanced but left heavy. Rotating at A gives us what we need because it moves this up to here. These are now all equal. Same thing going in the other direction. This is out of balance because this one is 2 shorter than this one. A single rotation at this point moves this tree to be the new child of C, and that gives us a balance. If we have this jagged situation, so it's right heavy at the top and left heavy at the second level, we need a double rotation. So this is a +2 out of balance, and this is -1 in balance but left heavy. Then we need a double rotation, one at C, a right rotation at C, which gives us this tree, and then a left rotation at A, which gives us this tree. And one of the things to notice is this difference is, sorry, I got the signs inverted. Let me take a deep breath. Try this again. I don't know why, I'm discombobulated today. Okay. The difference, this is T0, this height is T1 and T0 are the same, +2. So this is something minus something bigger than 2, this is -2. But this, B is 1 taller than the subchild at B is 1 taller than the subtree at T3. So this is +1. So their signs are different. Then first we're going to rotate at C, which makes their signs the same. This is +2, and now this is, or sorry, this is -2. I really wanted to have that inverted. That makes their signs the same. This is -2, this is -1. So it didn't actually solve our problem, but it made the signs the same. So now that when we rotate back, we get everything working. And if we look at this side, we had the same thing. So this is -2, this is -1, so the signs already agree. Same thing here, C is +2, B is +1, the signs already agree. In the double rotations, the signs are different. And it's when the signs are different that tells us it's a jagged stick instead of a straight stick. So the same thing will happen here. The height of C's left subtree is 2 greater than the height of its right subtree, but the height of A's left subtree is 1 smaller than the height of A's right subtree. So because the signs differ, we need a right rotation at A, which gets us to, or sorry, we need to, sorry. I need to slow down. Okay, we need a left rotation at A to get B back to swap A and B. That makes this +2. This is now +1 because it's left heavy, not right heavy. And then a right rotation at C solves the problem for us. So the intuition is when we have a +2 or a -2, if the heavy side has the same sign as the unbalanced node, we just need a single rotation. If the heavy side has a different sign than the unbalanced node, we need a double rotation. So this is an example just sort of in pictures. And this picture is going to turn out to be really, really helpful for you as you think about how to reason these things through. So if it's heavy left and heavy left, then a single rotation to the right solves the problem. If it's heavy right and heavy right, then a single rotation to the left solves the problem. If it's heavy left and right, then we need a rotation to the left to make it heavy left, heavy left. Well, once we have heavy left, we know how to solve that. If it's heavy right, heavy left, then we're going to rotate to the right to move the heavy side to the right. And heavy right, we know what to do there. Oh, Ian, that's very, very clever. I wish I had thought of that. So this picture is going to come in pretty handy for us, and we'll refer back to it both as we reason about this and as we think about things for the remainder of our conversation. Okay, so here's the basic idea. The basic idea is that we're going to insert, which is just this recursive descent insertion, and then as we unwind on the way back, we check the balance and rebalance if it's broken. So the outermost if the balance is greater than +1 or less than -1, we need to rebalance something. Okay. Additionally, remember, if +1 means it's left heavy, -1 means it's right heavy. So if the balance of the left child is negative, which means it's right heavy, then we have to do an extra rotation, which rotates the rotate left at the left child. And then once we do that, we're guaranteed to have a stick, and then we rotate right at the top. The same thing in the else condition. If the balance is less than -1, that means it's left heavy. If the right child is positive, which means it's right heavy, then we have a jagged stick. So let me erase the stuff that I was using to illustrate because I'm now over the text. So the idea is that the outermost if, which is this part, is the node out of balance? And if it's out of balance by more than 1, then it's left heavy and the left is too big. If it's out of balance by less than -1, then it's right heavy and the right is too big. If the left is too big, we're going to rotate right to fix it. If the right is too big, we're going to rotate left to fix it. Then the inner ifs are, do we need a double rotation? And that is, again, only if the signs of the balance check disagree. Okay? And if the signs of the balance check disagree, then we have to do this double rotation. So again, we have a tree. We're going to recursively descend down to the tree until we find the place to insert, and then we're going to walk our way back up. We're going to update the height of the, as we unwind the recursion, we update the height of every recursive node, and then we call check and balance on every node. So the first question is, what's the time complexity of this? At each step, we have a couple of comparisons and a couple of rotations. And remember, the rotations are fixed time because they only involve a couple of nodes and 3 pointers. So the rotates are constant time. And the comparisons are also constant time. So every check and balance is constant time. So as we're moving up at each level, it's constant time. So the real question is, after we insert something, what are the largest number of fixes we can possibly need? Now, we needed logarithmic time to find the place to insert. Even if we needed as many fixes as possible, it would still be constant time on each time on the way up. It's still logarithmic on the way back. But it turns out that when we're fixing things, when we add a node, we increase the height of it most a left or a right subtree by 1. Rotations bring that thing into balance. From above, it doesn't change anything else. Okay. So here's an example that we're going to follow, and we have an animation to do this. So I'm not going to ask you to do this yourself because it'll take a while to actually walk through. But we're going to insert this set of keys into an AVL tree. We're going to rebalance if we need to. And again, this cheat sheet is really, really helpful. Hint, 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 hint. Really helpful. Hint, 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 hint. So here's what we're going to do. We insert 3, then we insert 2. 3 is still in balance. Then we insert 1. 2 is in balance. 3 is out of balance. Rotate right. Insert 4 and 5. 3 is in balance. 2 is in balance. Insert 5. 4 is in balance. 3 is out of balance. Rotate left. Okay. Now we insert 6. 5 is in balance. 4 is in balance, but 2 is out of balance. Rotate left. Now we insert 7. 5 is out of balance. Rotate left. Everything else is fine. Now we insert 16. Everything is still in balance. Now we insert 15. 7 is out of balance, but it's inverted, so we need a double rotation. Everything else is balanced on the way back up. 14, 7's in balance, 15's in balance, 6 is out of balance, but it's jagged, so we need a double rotation, and everything is in balance on the way back up. So this is the final tree we get when we insert that set of things into our tree, and if you look at it, it looks pretty good. You know, it's kind of bushy, it's not very tall, and it's approximately logarithmic. And this website is very, very handy for being able to visualize how these sorts of things work as you're trying to make sense of it in your head. Okay, if an AVL tree is a binary search tree that says balance without any time trade-off, why use a plain binary search tree? And the answer is you never do. You could maybe use a plain binary search tree if you know for sure that your input is likely to be random. Not actually likely, that your input is going to be random. If you know your input is random, then you don't need to do the checks on your way back up. And that's what Blake is referring to, is that you pay the cost. But in general, you really don't. So for example, an ordered map is implemented with basically an AVL tree because it provides this. the basic idea is that the cost of the rotations to retain the balance is more than paid back if you happen to have a bad set. When you need to fix the tree, do we progress from the bottom up? Yes. So remember, these are recursive algorithms. So to do the insertion, you recurse down the tree, and then as you unwind the recursion up, you fix heights and balance factors and rebalance. Okay. Removal. Removal is even a little more tricky, and I know we're running short of time, so but I do want to work through this. For removal, remember that all of the keys are in the left-hand subtree are less than all of the keys in the right-hand subtree. So what we're going to do is rearrange the right-hand subtree so that its smallest node is in its root. There has to be something, since the right-hand subtree was not empty. The new right-hand subtree root has a right child but no left child. Then the right-hand subtree's root is the left-hand subchild of the left-hand subtree's root. So we take whatever this node is that has nothing to its left. We make this the new root of this tree. And then we can get rid of this. This becomes the new left-hand side. And then once we do that, we just have to rearrange the tree to balance the height. So wherever we removed, we have to go up the tree. Now, at every unbalanced node that we encounter, we have to rotate as needed. And what's really interesting about removal is that insertion only makes one subtree somewhere one deeper. So the only unbalance is in one place. A removal may remove from the shortest subtree pair of the shortest subtree pair of the shortest subtree pair of the shortest subtree pair. So removal may actually cost you a lot. So if we were going to remove node 32, well, 17 is balanced, so that's okay, but 44 is unbalanced, so we're going to have to do a rotate. And it's actually unbalanced. It's unbalanced even. So we remove 32, then we rotate left at 44, which moves this subtree as the child of child of 44, and this is balanced. So we have to keep doing this up to the root. This happened to be the root, so it was pretty simple to do. But we might need to fix something at every possible spot. So if suppose we wanted to remove 62, we find the in-order successor. The in-order successor is 78. We copy 78 into the node. We remove 78 from the right-hand subtree and replace it with its left-hand subtree. But now again, we need to balance. So we need to rebalance this way. And we actually need to do a double rotation, because if we just did one rebalance, we would just swap this tall subtree for another tall subtree over here. So instead we need two. We're going to rotate left at this child and then rotate right. So this is the rotate left. This is the rotate right, and 50 becomes the new node. And we have a really nice balanced tree when we're done with that. Okay, so remember, a fix shortens a subtree that's too tall. But if we're moving something, it may make something too short. So we're not actually fixing everything all the way. So when we're inserting, the new node is the source of the too tallness. It only makes one of those sides too tall. A single rebalancing will fix it. When we're removing, the deleted node can only create an imbalance, making subtrees shorter because we're removing something. But it could be already the shortest, so it might make something shorter and shorter and shorter and shorter all the way up. And so we have to fix it potentially all the way up. But again, each fix is constant time, there's log n levels, so it's log n total time to do the rebalancing. If we were going to remove this 4, I don't know why I lost the animation. I'll put a link to an animation in this too. There we go. Let's try that. There we go. That doesn't seem to work. That's funny. When I tried it earlier, it worked. So I apologize. But we are running short on time. We're already 5 over. Oh, no, it does work. I just didn't give it enough time. So we're removing the 4. Three is out of balance. It rebalances. Now we're going to go back up. 5 is out of balance. We need to do a double rotation to make that work, or a single rotation to make that work. 13 is out of balance. Rotate. And now we're good. So in this example, we had to rotate every single layer that we went up. So very useful website to be able to do all of these rebalances. Close the help, click on the AVL tree near the top, and you can insert and remove trees at once. Speed it up, slow it down. Very, very useful, useful thing. Oh, good, Blake. I had forgotten that it uses red-black trees, and we'll talk about that maybe in a Piazza post as well. So this is a pretty complicated lecture. I'm gonna just sort of finish this by saying this one's a little subtle. So it is worth spending more time thinking about this lecture. As you can see, even I'm still stumbling over it. And I went over it pretty carefully last night and again this morning, and I still got some details wrong. So that should be a hint that this stuff's a little bit more complicated than the average thing that we talk about. So I do encourage you to spend a little more time thinking about this lecture and reviewing the material in the text than maybe some of the others. This is also my last lecture with you, so I've really enjoyed this. As a little plug, I'll be teaching 482 in the fall, so if that's next on your radar, please feel free to join me there, and it should be a lot of fun. So it's been great. I'll see some of you in office hours. Good luck in the rest of Project 3 and in the rest of EECS 281. And I'll stick around for questions that anyone has for the next couple of minutes. All right, the question is, can I go back to slide 92? So remember that when we're checking and balancing, we're going to insert something, and then on the way back up, we're going to update the height of the node and check and rebalance. The time complexity of the insertion is logarithmic because it's logarithmic in height. At each step, we're going to update the height. That's a single operation. We're going to check and balance. That's a constant operation. And we're going to do that logarithmic times. So the total time for insert to go all the way down, add the node, and all the way back up is logarithmic, no matter how many fixes we need. And it turns out for insertion, we're only going to need one fix because rotation shortens the largest subtree and insertion makes one of the subtrees longer. By rebalancing, we shorten the longer subtree, which means that the overall height of this node stays the same as it was before. So if we're doing a rotation on a node, its height is guaranteed to be the same. Since its height is the same, everybody above it remains in balance. So if this node doesn't rotate, then its height might differ, but then somebody above it will be out of balance. And when it does, everything above that will be in balance. So for insertion, you only need one fix on the way back up. You need to update the heights everywhere, and you need to update the balance factors check the balance factors, but you only need to fix one of them. Nicholas, what are the benefits of a tree versus a vector? Well, let's talk about what the downsides are. Vectors fit in contiguous memory, so they're very cache efficient. Vectors have random access through the index operator, so if you need a random, something at index 42 from a vector, that's really easy to get. Trees have the advantage that they are always sorted. Particularly binary search trees are always sorted. Now they pay a little extra overhead in the pointers for that, but they make sure that all of their things are always sorted. And AVL trees, or another kind of tree, red-black trees, which I don't think we're going to talk about in 281, but it's another version of this self-balancing tree idea. Those trees are always guaranteed to be logarithmic in depth. So insertion and removal is always logarithmic, as opposed to vector, where if you're inserting something in the back, it's constant time, but finding something in there is linear. Finding something in the search tree is logarithmic. So one of the things that I think we're going to see at the beginning of next lecture, if I remember correctly, is just a quick review of some of this, but I will also come back for that. And so I think I have a couple things on Piazza to talk about. It's trying to remember what they were, but it's comparison of runtimes, pros, cons, and of tree versus vector, and maybe I'll do a couple more as well. And Michael, you're welcome. All right, it looks like most people have filtered out, so I'm going to go ahead and end the stream. Again, thanks a lot for joining me, and enjoy the rest of 281, and hopefully I'll see you in 42 in the fall.